Okay, so welcome to this third video. This one is about mole calculations. So one of the basic types of calculations that you're going to have to do. This is all about how reacting amounts of substance. So if you want to make 10 kilograms of this particular chemical, how much reactants do you need to do that? That sort of thing we're going to look at. Okay, so mole calculations. First of all, you might be wondering, well, what is a mole? It is a furry creature that lives and burrows tunnels, but in the context of what we're doing, it's actually an amount of substance. And 1 mole contains 6.022 times 10 to the power of 23 particles. Okay, so when I talk about numbers of moles or a number of mole of something, what I'm saying is a number of particles. But rather than counting it in terms of individual particles, I'm talking about in terms of multiples of 6.00 times 10 to the 23. And that's an enormous number. I mean, it's a seriously enormous number. And the reason why we count things in a seriously large sort of packet, if you like, is because there are a lot of atoms and molecules in the amounts of chemicals that you'll weigh out in the lab, or anybody will use in the lab. You won't typically be using individual molecules or atoms ever, but what you will be using is 5 or 6 grams of something, and within 5 or 6 grams of something there are billions upon billions upon billions of particles. And in chemistry, a lot of the time we need to know how many particles there are. So rather than talking about the absolute number of particles that we've got there, we talk about it in terms of multiples of this number. That number is called Avogadro's number, the 6.022 times 10 to the power of 23. Okay, and if you have a mole of something, you'll have that many particles. Now, when you look at a periodic table, what you'll find on a periodic table is that you've got two numbers. If I do carbon, for example, you've got a 6 down here and you've got a 12 up there. If you look at an accurate periodic table, you'll find that this number is actually slightly higher than 12. Why it's slightly higher than 12 we'll come on to later. But that number there is the mass of 1 mole. So if you had 12 grams of carbon, you would have 1 mole of carbon atoms, or literally you'd have 6.022 times 10 to the 23 atoms sitting there in that pile of 12 grams of carbon. So if I do a little table here, mass, element, moles, particles. So if I had 12 grams of carbon, I would have 1 mole of carbon, and I'd literally have 6.022 times 10 to the power of 23 atoms. On the other hand, if I take the lightest atom, hydrogen, the top number, or the one that's called the relative atomic mass, okay, these are relative masses, so they're compared to a standard, and the standard is actually carbon 12, and it's the mass of 1/12 of the carbon 12 nuclei, the carbon 12 isotope. We'll come on to the definition of why you got that definition later on. But the relative, so they're compared to one another. So a hydrogen atom is actually only a 12th the mass of a carbon atom. So if I had 1 gram of hydrogen, I'm talking literally individual hydrogen atoms here rather than H2, I'd have 1 mole of hydrogen atoms and I'd have the same number of particles. So 1 gram of hydrogen has exactly the same number of atoms in as 12 grams of carbon, because carbon atoms are heavier. So if I look at, I don't know, something like oxygen, which is 16, which literally means 16 grams of oxygen is 1 mole and has that many particles in. But if I only had 8 grams of oxygen, I'd only have half that number of particles, so I'd have half a mole, and I'd only have 3.011 times 10 to the power of 23 particles. I'd have half the number of particles. If I had 6 grams of carbon, I'd also have half a mole and I'd have the same number of particles. Carbon atoms are not quite as heavy as oxygen atoms. To give you an extreme example, uranium is 235, thereabouts. So if I had 235 grams of uranium, I'd still only have 1 mole. That's because uranium atoms are 235 times heavier than hydrogen atoms. So I'd be back to 6.022 times 10 to the 23. Okay. From this you can deduce a relationship. Okay. And this is a really important relationship. The number of moles of literally anything is equal to the mass in grams that you've actually got. So this mass here, okay, divided by what we call the molar mass. Okay, in grams. Okay, this is the mass of 1 mole of something. So that's how heavy is, the mass of 1 mole of that substance. Now if that's an element, then you get it straight off the periodic table. Okay, so it's this number here. So that, in the case of an element, is that number there. If you're looking at a molecule, okay, so CH4 for example, what you've got to do is sum the relative atomic masses of the individual elements. So that would be for carbon 12, for hydrogen, because you've got 4 hydrogen atoms there, it's 4 times 1. Add those together to get 16. So the mass of 1 mole of a methane molecule is 16 grams. So if you had 16 grams of methane, you'd have 6.0022 times 10 to the 23. So I've had CH4 there, it would be 16 grams, that would be 1 mole, 6.022 times 10 to the 23 again. Okay. So this is a way that you can work out how many moles of something you've got. Now in terms of chemistry, that means how many particles have you got. Okay, so rather than thinking about this 6.022 times 10 to the 23 business, which you will seldom ever have to use, certainly not in the context of this type of moles calculation, what's going to be important is the mass of stuff that you've weighed out and how heavy is 1 mole of it, which you can get from its formula. So you can work out a number of moles from mass and a molar mass. The other thing that you'll frequently have to do with this equation is rearrange it to work out the mass of something you've got. So mass will equal the number of moles let me just go to the right a little bit. Number of moles times by the molar mass. So if you know how many moles of something you've got, okay, and you know its molar mass, you can work out how much you've got, literally how much you physically got in terms of its mass. So this here, and the other way of writing it here, it's going to be probably the most used equation that you'll use in chemistry. Now there are variations of it which work for different states of matters, things like gases and solutions and stuff, which will come up against later, but we're not worried about that now. We'll do those when it's appropriate. So let's just look at how this relates to doing something vaguely useful. So we're talking about methane here. So if I take CH4, react it with oxygen, and we had this equation in one of the earlier videos, whoops, to make CO2 plus H2O. Now it's important to have a balanced equation, absolutely critical to have a balanced equation. So we've got 4 hydrogens here, so we're going to need 2 waters there, and because we've got 4 oxygens over here, we're going to need 2 oxygens over there. The reason that that is really important is because it literally tells me one methane molecule would react with 2 oxygen molecules to make 1 carbon dioxide molecule and 2 water molecules. But in the real world, we're not talking about individual atoms or molecules in this case. We're talking about measurable amounts of stuff. And measurable amounts of stuff is measured in moles. So this is literally what 1 mole reacts with 2 moles to make 1 mole and 2 moles. So if I had 6.022 times 10 to the 23 molecules of methane, I'd make 12.044 times 10 to the 23 molecules of water. I'd make double the number of molecules of water. But we don't talk about these big numbers, we don't need to, because we're talking about the number of moles. So let's suppose I started with 16 grams, let's keep it really easy to start with, 16 grams of methane. 16 grams of methane is 1 mole. Okay. So I'm going to make 2 moles, so that is 1 mole. Okay. So I've got 1 mole of methane. I'm going to need 2 moles of oxygen to react completely with that 16 grams of methane. So if we look at our equation over here, how much oxygen do we need? That's mass equals the number of moles. So here the number of moles is 2 times by the molar mass of oxygen. Now the molar mass of oxygen is O2. It's going to be based on O2, so that is 16 times 2, which is 32. So 2 times 32 is 64. So if I'm going to burn 16 grams of methane, I actually need 64 grams of oxygen to do it. If I do the same thing for the carbon dioxide, I've got 1 mole, because we know we've got 1 mole of methane, so 1 mole of methane will make 1 mole of carbon dioxide. And I've got to multiply that by the molar mass of CO2. So that's 12 plus 16 times 2. So that's 32 plus 12, that's 44. So I'd make 44 grams of CO2. So if I burn 16 grams of methane completely, then I'll make 44 grams of CO2. In terms of the water, water is 2 times 1, whoops, if we add on 16, that gives us 18. So this is going to be 2 times 18, because we've got 2 moles of it. 1 mole would be 18 grams, 2 moles is 2 times 18, which is 36 grams. So by doing this moles calculation, we know we start with 16 grams of methane, we're going to make 36 grams of water, and we're going to make 44 grams of CO2, and we're going to need 64 grams of oxygen to bring that about. Just to do one other example, which doesn't have quite such easy numbers perhaps. Let's burn some hydrogen to make H2O. Now again, to make this balance, I'm going to need to put a half there. Okay, so this equation is telling me if I had a mole of hydrogen, that would react with half a mole of oxygen to make 1 mole of water. So let's suppose we had 27.5 grams of H2. How much water would we make and how much oxygen would we need to burn it? So what you've got to do is work out how many moles of hydrogen you've actually got. And remember, the number of moles is equal to the mass you've got, which is 27.5, divided by the molar mass. Now this is H2, so there's 2 hydrogen atoms joined together, so the mass of H2, the molar mass of H2 is 2. Like that. Okay. This equation is telling me if I have 1 mole of hydrogen, I'll need half a mole of oxygen. I've actually got this many moles of hydrogen, but the reaction ratio is the same, so I'm going to need half the amount of oxygen. So the amount of hydrogen I've got is 27.5 over 2, and I've got to multiply that by half. Okay, so I'm going to have half that amount of oxygen. Yeah. To make the water, this is a 1-to-1 ratio. So if I've got that much hydrogen, I'm going to have exactly the same amount of water being produced. If I want to know the mass, this is just the number of moles. Remember, the mass is equal to the number of moles times the molar mass. So I'd take this and multiply it by the molar mass of, in this case, oxygen. And oxygen has a molar mass of 32. Here I'd take that and multiply it by the molar mass of water, which is 18. Okay. Now this one, I think I'm going to struggle to do in my head, so I'll have a go on a calculator. 27.5 divided by 2 is that, times by 0.5 is that many moles, times by 32. So that would be 220 grams of water, oxygen needed, and the other one is 27.5 divided by 2 equals that, times by 18, 247.5. Okay, so if I took 27.5 grams of hydrogen and burnt it completely, I'd make about 1/4 of a kilo of water. You're making a lot more because you're adding the oxygen to it, and the oxygen atoms are much heavier than the hydrogen atoms. Okay, that's a very brief introduction to moles calculations, but it just gives you a flavour of what it's about and the basic principle behind it. You can watch that as many times as you want, and we'll go over some of those sorts of things in the lesson, but it's that type of calculation you've got to get your head into gear with very, very quickly.